after the point defects, we will move on to the line defects. Now, these line defects are one-dimensional defects that are present in a crystal structure. Now, in this case, a whole line is dislocated. Okay, so a dislocation in this is like in the whole line is there, and the discontinuity is in the regular crystal structure is there. Okay, so that is why it is a line defect. Now, a part of the line, it might be missing from its regular site, and this missing row is known as your dislocation. Now, this dislocation is centered along a line. So there is one line, and along that line, this dislocation is centered. So hence, this is also that's why the name is dislocation here. Now, the structure and the behavior of dislocation affects the different properties of the materials. So there are two types of dislocations are there. Line defects are there. One is your edge dislocation, and the other is your screw dislocation. Now, in the edge dislocation, so here you can see both the types of dislocations are there. So in this, we have a edge dislocation. In this, you can see that at the bottom there is this normal crystal structure is there, and from this 1, 2, 3, fourth line, a new row of atoms is added inside the crystal structure. Now, what this does is this pushes the other atoms in the outward direction. So here you can see the distance at the bottom is small, and as we move upwards up to this fourth row here, the distance is more here. So the atoms get pushed, and this forms a dislocation that is known as your edge dislocation. And then a screw dislocation is on the right hand side. This diagram is your screw dislocation. So this is along a say a row, and in this what happens is the dislocation of atoms is in the form of helical or spiral along a dislocation line. So there will be a common dislocation line, and along that line a twist or helical movement of your like in a torsion, you can say, when the metal crystal is in torsion. So if we rotate both the ends in opposite direction, okay, so that type of dislocation will be known as your screw dislocation. Now, if you look at this edge dislocation, now in this what happens is the edge dislocation in a metal, it may be because of the insertion or removal of an extra half plane of the atom in the crystal structure. So you can say that on the top part, if this is your in the diagram below, so this is your normal crystal structure, and in the bottom there is one of the columns that is missing. Okay, so this is your where the edge has been removed, or in opposite, you can say that on the top there is one edge that is added. So both types of dislocation is known as your edge dislocation. Now, the ionic and the covalent solids edge dislocations involve extra half plane of unit cells. Okay. So in the diagram on the right hand side, you can see that there is one extra half plane or a plane has been added. If we consider a perfect crystal to be made up of a vertical planes or parallel to one another and to the side faces, if one of these vertical planes does not extend from the top to the bottom of the crystal but ends part way within the crystal, it is called edge dislocation. So this you can see in this crystal structure. So this is a parallel line, so all the atoms are in a line. Okay, so this this line continues, this line continues, this line continues, and the middle line you can see that this discontinues. So the atoms are missing after the third line. So this type of dislocation is known as edge dislocation. So one of the edge is dislocated or missing from the crystal structure. And this edge dislocation is denoted by this sign of perpendicularity. Okay, so where the edge dislocation is there, we designate it with this sign here. And the Berger vector, so hence because it is a perpendicular sign, the Berger vector, it is perpendicular to the dislocation line. Okay. So the Berger vector is perpendicular to the dislocation line. So that is why we designate it with this sign of perpendicularity. Now the movement of edge dislocation, how the edge dislocation it moves within the crystal structure. Okay. So this is under the effect of shear. If we put the top part of this crystal structure and we push this top part, bottom part is stationary. Okay, so what will happen here? The one of the rows it will move in the outward direction. Okay, so this in this diagram you will see that this edge dislocation, that this row it moves in the forward direction. So when the force is applied, so this row it is pushed in the right hand side direction, and this dislocated row or the column it moves forward. Okay. So the atoms they get bound onto this side, and you can see the first this dislocation was in the second column. Now it is moved to the third column, then it moved to the fourth column, then to the fifth column, and then to the outwards is there. Okay, so this is how the dislocation it moves inside a crystal structure when loading takes place. Next type of dislocation is your screw dislocation. Now in this screw dislocation, there is a transformation of successive atomic planes into the surface of helix around the dislocation line due to the shear stress, and it follows a helical or a screw path. Now the screw dislocation, it can be imagined as being produced by cutting the crystal part way through with a knife and then shearing one part of the crystal with respect to the other that is parallel to the cut. And this also can be compared to a spiral staircase whose central pillar coincides with the screw dislocation line. So here you can see that now here if the upper part of the body, or if the two ends, that is top and the bottom, they are say twisted in opposite direction, so there will be a central plane around which the dislocation will start. Here you can see that this at point A and D, the dislocation is there. So that at the weaker point, the dislocation will take place. So A, D, and C, and on the other side, you can see that the dislocated plane. You can see. So here is this plane is your the base plane around which the twist has taken place. So in this, what happens is the Berger's vector, it is parallel to the dislocation line. So this type of dislocation is known as your screw dislocation. Next type of defect is your planar or surface defects, and these are also known as two-dimensional defects. The planar defects arise due to the change in stacking of the atomic planes during mechanical and thermal treatment. Now the change may be of the orientation of the stacking sequence of the planes. Okay. So when some mechanical or thermal treatment is given to the crystal structure, okay, so the different layers or the stacking of different layers that gets distorted, and the defect is known as your planar defect, because the defect is in the plane of the crystal structure. Now these planar defects are of three types. There can be grain boundaries that may be caused, tilt boundary might be there, or there will be twin boundaries there. Now if you see here in the grain boundary, so here you can see that the atoms in one of the grains, they are in order, In another plane, they are also in order. In the third plane, they are also in order. But what is happening here is that the orientation of these atoms is different from that of the other atoms. Now, this orientation, where it changes, the angle where the orientation of the atoms it changes, it forms a boundary here. Blue line, you can see this line, it separates one of the region from the other region. In one region, all the atoms they are aligned in a definite pattern, but in different orientation. The angle is different. So all these are divided by some boundary, and this boundary that divides these planes that are or the regions that have the separate orientation of atoms, but in different orientation. Okay. So these are known as your grain boundaries there. So grain boundary is formed. So a grain boundary is a general planar defect that separates regions of different crystalline orientation within a polycrystalline solid. So the grain boundaries are usually the result of uneven growth when the solid crystallizes. So this is your grain boundary defect. Second type is your tilt boundary. Now here you can see that on the right hand side, the crystal structure, they are or atoms, they are arranged in proper order, and then at certain point, one of the rows has missing atoms, and then again there is one more row, there is missing atoms. Now this, what it does is it tilts the structure or the pattern of atoms, okay? And all the atoms they are not now in parallel. So there is some tilt that takes place. So this causes your tilt boundary, okay? And the tilt boundary is denoted by this sign here. Okay? Now, when the angle between two crystals is less than 10, the distortion is not so drastic as compared to a non-crystalline material. They are also called low angle boundaries. It can be described as set of parallel, equally spaced edge dislocations of same sign, okay, located one above the other. Now, a tilt boundary between two slightly misaligned grains appears in an array of edge dislocations. So it forms an array of edge dislocations. Or other tilt boundary is also caused by when two adjacent crystalline grains, they are say tilted relative to each other by a few degrees. Now, if the angle is less than 10 degrees, so then the tilt or the boundary that is formed is known as your tilt boundary. Okay. And then the third one is the twin boundary is there. Now, in twin boundary, what happens is this boundary here, it separates two crystalline regions. So there is one crystalline region and there is another crystalline region. Now these both crystalline regions, they are mirror images. Okay, so atoms, if you place them, they become mirror images. Now, such a boundary that separates, say, the two crystalline regions that are mirror images to one another, such type of boundary is known as your twin boundary. Now these, you can say here by the definition here, now these are the boundaries in the grains at which the atomic arrangement on one side of the boundary is the mirror image of the atoms on the other side. Now the volume of the material which has an orientation similar to the mirror image of the matrix orientation is called a twin. Now this, the plane that separates these two mirror images is known as the twinning plane. So this is your twin boundaries there. Now next is your three-dimensional defects that are known as your either surface defects. Now surface defects, they are associated with the boundaries that are separated, separate regions of the materials and have different crystal structure. So these are also surface defects are also two-dimensional defects. These can cause because of a change in orientation of the atomic plane and stacking sequence of the atomic planes, and these are caused during solidification or mechanical or thermal treatment of the material. Now, the effect of mechanical properties or electrical resistance and corrosion resistance. Uh, so these are the properties which are affected by the surface defects or the planar defects. Next comes is your bulk or volume defects. This is your three-dimensional defect. Now, precipitates, there are some definitions. What are precipitates? Precipitates are fractions of a micron in size. This percents can also be there. Maybe large precipitates, grains, or polygranular particles that are distributed throughout the microstructure of the crystal structure. Inclusions. In inclusions, what happens is foreign particles or large particles uh, or undesirable or harmful particles, they come inside the crystal structure, and these impurities or defects are known are due to the inclusions. And then the voids. The voids are when the crystal structure is being made, and when the crystallization starts. So if there are some trapped gases or pockets are formed inside, so that gap, it forms a void inside the crystal structure. Uh, this decreases the mechanical strength of the crystal structure. So on this diagram, you can see that there are micro cracks inside the granules. Okay. So these are your micro cracks are there. These happen when the solidification of the crystal structure or the formation of the crystal structure is taking place. Now, volume defects such as stacking faults may arise when there is only small dissimilarity between the stacking sequence of close packed planes in FCC or HCP metals. Stacking faults are of two types. They are intrinsic or extrinsic. Now, intrinsic faults results in one break, whereas in extrinsic faults results in two breaks in the sequence. Okay. So intrinsic means internally, and extrinsic means by outer factors are there. And the volume defects, they may affect the mechanical, electrical, and optical properties of the. So these are your volume defects. Okay.